Good morning, everybody, and welcome back to Abstract Algebra. Just so you know, I put a handout over by the door. Make sure that you have a copy. Plan for today, before I forget, let me do the joke. Why did the yardstick want his parents to stop supporting him financially? It's because the yardstick wanted to stand on his own 3 feet. Okay, so the plan for today is we're going to start talking about Chapter 3, where we will be looking at subgroups. Upcoming office hours are no more office hours today, but I will have office hours in the hour before class on Monday and 2 to 3 Monday. I'll send out a poll in the next day or two where you'll be able to sign up for office hours for next week. Right now you can't. As far as homework goes, don't forget, first homework due at 11:59 p.m. tonight. Also, the second homework is now posted on Blackboard and will be due Friday night a week from now. So in general, whenever I'm not going to keep writing this down on the board, but whenever I say a homework assignment is due on a particular day, it's always going to be at 11:59 p.m. that day. So 4 days, and so you have the full day to complete it and turn it in. So. But yeah, homework 1 is due tonight. Homework 2 is going to start including a few proofs, like the ones we kind of have done the last couple classes, as well as we'll be doing some more proofs next week. Homework 2 will be a mix of a little bit of computation, and do you understand some examples, and a little bit of can you prove certain things. For instance, homework 2 is going to have the question where you have to prove that if you look at the Cayley table for any group, it contains every group element exactly once in each row and column. That'll be a homework 2. That's a homework 2 question. Any questions or comments before we get started for today? Groovy. Let's do some math. So, next couple classes, we're going to be talking about subgroups, where a subgroup is a little group that lives inside of a big group. Basically, it's just going to be a subset of a group G. Subset H of a group G that itself forms a group under the operation of G. So, thought we would start off by just looking for a few examples. So, if we look at the integers, I claim either the odd integers or the even integers, but not both, will form a subgroup of the integers. So, if we look at the set of all odd integers under addition, and if we look at the set of all even integers under addition, I claim one of these two will be a group that forms a subgroup of the integers. Which one of these do you think will itself actually form a group structure? No, Jackson?
Depends on whether you're calling 0 an even or an odd number.
0 isn't even.
Okay, some people call it, yeah. So
some people are wrong.
Sorry?
Some people are wrong. Continue.
Anyway, you need the identity element, so odd can't be a group.
Yeah. So this one is going to fail to be a group, since it has no identity element. It also doesn't have closure. I could take 2 odd integers, like 1 and -3, add them together, I'll get -2, which is not an odd integer. But the set of all even integers, which has a fancy name, I'm going to call it 2z, just the set of all integer multiples of 2. That's, by the way, how I'm going to define an even integer. An integer is even if it's an integer multiple of 2. And it turns out it's going to turn out to be the case that 2z, the set of all even integers under addition, will form a group, and in fact, this will be a subgroup of the integers. Subgroup meaning it's a smaller group that lives inside of a bigger group under the same operation. What's the identity of 2z? We say 2z, the set of all even integers, is a group.
0?
Yeah, 0 is going to be the identity element. It's going to be the same identity element as the larger group. Inverses are going to work the same way as the larger group. It's just whatever the inverse of an integer is in the larger group, assuming it's an even integer, the inverses are still going to work out to be the exact same way. So x inverse equals negative x for all elements x in 2z. We still have associativity because since integer addition is associativity in general, if we restrict ourselves to looking only at even integers, it's still going to be associative. The exact same operation, but just fewer choices for what A, B, and C could be. And it's also going to be closed in that if you add any two even integers, you're also going to get an even integer. So in general, when we're looking for subgroups, we're just looking for this sort of behavior. Smaller groups that live inside of bigger ones. And subgroups are going to be very important to us throughout the semester in that they're going to give us a large class of examples to look at. Subgroups of GL2R, subgroups of the integers, subgroups of other things that you may have determined were groups on homework 1. What I would like for you all to do, take a look at the first page of this packet, and I would like for you to try to find 2 examples of subgroups for each of the groups that I gave you. Integers under addition, real polynomials of degree less than or equal to 3. Spoiler alert, if you haven't finished homework 1 yet, that one's a group. And the dihedral group, D3. What I challenge you to do is to see if you can find 2 examples of subgroups for each of these 3 groups. As always, if you feel comfortable, you can talk to the people sitting around you. If not, please don't. And have fun with that.
So polynomial less than or equal to 3, and multiplicate is less than or equal to 2 is subgroup, right?
Yeah. That's more key creative. We get to go for that.
Probably. What about 4z?
4z?
Right, so multiples of 4 is multiples of 2. You know, say multiples of 4 and you get
They do.
Is that always going to be a group of like?
If you forget what the polynomials of degree less than or equal to 3 look like, here it is written out in set notation, just
what?
things that look like ax cubed plus bx squared plus cx plus 2.
Well, because doesn't like multiple densities. That's
that's
the
true.
shifted over one. Like that's the plus one rather than c times something.
There's always that issue with the closure. It just has like x and then
This
negative.
is
If you
multiple.
have-
Because 3 times
Yeah.
0
So you always have to be less than.
So any
But we think that
Any
you really should
n
be one or.
z where n is an element
I
of
would
the
think so.
Yeah, it wouldn't be much fun. Yeah.
Oh,
But it wouldn't be legal.
we can make it a
What's
natural.
not legal?
It is
Yeah,
legal.
there's a
What is it?
multiple by zero still works with it.
Wouldn't you also do just the integer?
Yeah.
Whatever else.
Is it?
Everything that is not illegal is legal.
We were talking about P with this E0.
What about D3? I feel like that's a tougher one.
So just the set of all
You
constant
make
polynomials?
D2, is
Yeah,
that
which is
exists?
So in other words, the set of all real numbers.
Yeah.
D2 is a
Yeah,
line.
It's not the set of integers, it's the set of real numbers.
That you flip around, that's a group, right?
I don't see why not.
That exists.
They're the same, it's the group operation's the same.
Well, wait.
Well, I mean, a triangle is made up of
It
three
might,
lines. I don't know.
because like, degenerate triangles might be part of
This
D3,
is a subset.
and degenerate triangles just a line.
Oh, and these are under addition.
Well, what about like D3 with rotations only and no reflections?
What about D3?
Oh, well, you got identity.
Possible to do with like, with a
Um,
particular number.
I mean, you can undo everything.
So like with, is that?
Yeah.
And then you do the same with reflections.
Just set of all.
You only get, there are only two elements in the group, but-
Yeah.
There's not, okay, so
Wait,
there's
what
only
is
6.
the regular D3 operation?
You just do like.
You can like rotate in, like, for this one, we're saying you can do one or the other.
But for groups, there's always like one thing you can do, right? Like,
For those of you watching
can
this on
add
YouTube, I
multiply
encourage you to
and
be trying this
square or
along
whatever.
at home.
That's right.
What's
It's
binary
great, there's like
operations?
two
Jeopardy
operations.
music in the.
Yeah, what's binary
I'm
operations?
sorry?
Then you gotta have the Jeopardy music in the meantime.
Why are we allowed to use two
Do.
Can you cold call on your YouTube viewer? Just be like, ask a question and then say,
Yeah.
what do you think about it?
Actually, when I was recording classes this spring, I would do that a lot. I would just record classes like because I just pre-recorded lectures posted on YouTube with no students in the room. I would just frequently be like, I'd be like, Elaine, what are your thoughts? Elaine, what do you think about this? Oh, that's what you think, Elaine. Well, it turns out you're correct. What Elaine proposed was that blah, blah, blah. I would do a lot of that.
Let's do math class like Dora.
Can you find a way to...
Right.
Great. Swipe or no swipe?
Oh, man.
Actually, I don't think
Instead of like Dora,
I like that.
All right, let's take another minute or so, and then we'll come back together as a class and discuss what you found.
Okay, for the last one, we can
Binary
it's
operations
like
for
D2
the diagonal group.
I don't know.
D2 is not a thing.
It's a
D2 is
lot.
I was gonna say symmetries of the line. Well, yeah.
I mean, you
Like
could.
algebra sets,
Technically, lines don't count as polygons, so.
Okay, so I think we can do.
You just say no looking at kids. So that's a start.
So, remember the binary operation
I
was
think
for
there's just like
diagonal groups?
all the reflections, really only.
Thinking about it, I think a group is technically
Oh, yeah, so it's a
Yeah, which is represented by like R3, this is one. And then the rest is
operation would just be.
But there's two operations you already.
Yeah, like, remember
Oh my
what the
gosh,
binary
oh,
operation was for diagonal groups?
No, it doesn't make sense.
I
I mean, I don't know if it is, but I think that's why they're
it's
special.
reflected.
Because, but then a lot of groups.
That's a clue.
I'm pretty sure they're just supposed to be the ones.
I think it's like
Like
rotations and reflections are
rotate.
Okay, let's come back together. I want to come back together now and see what you all came up with as far as subgroups.
Yeah.
So, anybody find any other subgroups of the integers other than just the set of all even integers, 2z?
NZ, where N is in 2Z.
Where? Wait, so nz in general, or n is
In 2Z.
actually nz will always. You just came up with all of them. nz will always, in fact, form a subgroup of the integers, or n could be any integer.
Okay.
Works if n is even, but it also works if n is odd. For instance, the set of all multiples of 3 is going to form a subgroup of the integers. The set of all multiples of 5. The set of all multiples of -2. The set of all multiples of 5,746,372,189 will form a subgroup of the integers. In fact, this is going to be something we prove in chapter 4, is that all subgroups of the integers look like this. I forgot to mention earlier, the notation for saying H is a subgroup of G, sort of the symbol that you use for is a subgroup of, actually looks just like a less than or equal to sign. Which is a bit weird, but to me, but when we're talking about groups, H less than or equal to G, what we really mean is H is a subgroup of G. It's kind of the common notation. How about subgroups of polynomials of degree less than or equal to 3?
Couldn't you just say Z, group of all integers?
I was hoping to start bigger and work our way down to that, but yes, the integers will be a subgroup.
P is less than or equal to 2.
Before we move on, actually, I will say NZ will always form a subgroup of polynomials of degree less than or equal to 3 under addition. I hope it's not too hard to prove. I'm not going to prove it right here, but you can show that if A is a subgroup of B and B is a subgroup of C, then A has to be a subgroup of C. So any subgroups of since the integers are a subgroup of polynomials of degree less than or equal to 3, any subgroups of the integers will also be subgroups of this group. Also, polynomials of degree less than or equal to 2, just things of this form where A is equal to 0, that'll form a subgroup. Any others?
P less than or equal to 1.
P less than or equal to 1. Real numbers or the rational numbers, or I've seen homework 1, the set of all kind of things that can be written as fractions of integers. This thing has a lot of subgroups, it turns out. How about subgroups of the dihedral group, D3?
Okay, so we were thinking the group of only rotations, so like R squared, and then R cubed.
Okay, I'm going to write E instead of R cubed. Let's see. I think this has closure. This times this is in here, this times this is in here, this times this is in here. Everything times itself is going to be a rotation, so this has closure. It has associativity, it has an identity element, and I think it also has inverses, and that E is its own inverse, R and R squared are going to be inverses of each other. I think this checks out. The set of all rotations will form a subgroup of the dihedral group. And this works in general for any dihedral group Dn. The set of all rotations will form a subgroup. Any others?
How
Wrong?
about like E and S?
Well, let's see. S is its own, let's see. E times S is S. E times E is E. S times S is E. So it has closure. Associativity gets for free. Has an identity element. And I think it has inverses since E and S are both their own inverse. That one checks out too. The set that just consists of the identity transformation and a single reflection will in fact be a subgroup. Anybody find any others?
Can you say just the identity element?
Well, let's try. Does it have closure? Literally, the only thing we can try is taking E star E. Does that give us something back in the set? It gives us E. So it has closure. Associativity it gets because E star E equals E star E. It has an identity element. And I think it has inverses because E is its own inverse. It checks out. In fact, something on page 2 that we'll see, this is going to be a subgroup of every group. If you take the set that just contains the identity element, that's always going to give you a subgroup, no matter what group you're looking at. Even here, technically you could say 0Z is that subgroup that just contains the identity element, because the set of all multiples of 0 just contains 0. All right, before I move on, a couple more questions. What about this? Is the set containing 1 and negative 1 under multiplication going to be a subgroup of the integers? Why not?
I can't think that fast.
Well, you said you made a stand, so now you have to defend it. Does it have? All right, let's start. All right, well, I'm going to pick on you since you dared to speak up. Does it have closure?
Yes.
Yeah, it has closure. 1 times negative. Multiply any two things in here, you'll get back something else in here. I think it has associativity. It has an identity element, 1. 1 and negative 1 are both their own inverses multiplicatively, so it has inverses. So I'll ask you again, is this a subgroup of the integer?
I did say yes the first time, so yes.
Turns out the answer is no.
No?
Why not?
Wait.
And there is a subtlety here as to, I just said it satisfied all 4 group properties, but then said it's not a subgroup of the integers. So there's a very subtle reason, if you look carefully at the definition of subgroup, that says why is that not a subgroup of the integers under addition? Alex?
Not under the operation.
Yeah. In order to be a subgroup, it has to have the same operation as the original group. And here, this doesn't form a subgroup because it has multiplication, whereas the integers have addition. It is true that this is a group, and that the set 1, negative 1 is a subset of the integers, but it does not form a subgroup of the integers because it's not the same operation. Last question. The dihedral group D3 a subgroup of D4? Ron?
I mean, I'm just kind of thinking intuitively no, because like the triangles and squares are 2 different shapes completely.
They're not the same shape.
The rotations are defined differently.
Yeah, since the rotations are defined differently, in D3, we're looking at R, a single rotation R corresponds to 120 degrees, whereas in D4, a single rotation corresponds to 90 degrees. The rotations in one don't correspond to rotations in the other, so technically, the answer is no because, well, not even just technically. The answer is no because the operations are not the same. Even though you might say, but it's just composing, but in both cases we're composing symmetries, the fact of the matter is the symmetries in D3 are not the same as the symmetries in D4, and so it's not a subgroup. Any questions or comments about any of these? Rowan, nice observation there. Yes.
Would it be for that? Would it be that the operations aren't the same, or would it be that like like you define the different stuff differently? So like the r squared s wouldn't be the same in both of them.
That also holds true. Yes, it's not only like the operations are a little different, composure of symmetries of R4 and R3, but also the actual elements themselves, R and D3, does not mean the same thing as R and D4.
Okay.
So now, you can flip to page 2. Here is an example of a whole bunch of different types of subgroups. So first example is the improper subgroup. Fun fact, every group is a subgroup of itself. It's a subgroup called the improper subgroup because It's not proper. We don't like it. It's kind of a boring example of a subgroup. So G is always a subgroup of itself, and this is called the improper subgroup. Any other subgroup of a group other than the group itself is going to be called a proper subgroup. That's going to be an important distinction because we're going to have a lot of theorems later in the semester that say blah, blah, blah has to hold true for any proper subgroup of G. For instance, if we were to take all integer multiples of 1, well, that's just all the integers, since every integer is a multiple of 1. So 1z is the improper subgroup of z. Touched on it earlier, the set just containing the identity element will always be a subgroup called the trivial subgroup. Trivial also just meaning kind of another boring example of a subgroup because it holds true in any group and you can't really do much with it. So we're going to do more boring examples of subgroups of every group. A more interesting one is the center of a group, where the center of G is going to be the set of all elements A and G, such that AG equals GA for all elements G. So in other words, the center of a group is just going to be the set of all elements in the group that commute with everything else. And we typically denote this by just putting a G, or Z of G. Z standing for the word center. In German, at least.
So for the group with the integers defined under addition, then what would the center be?
Oh, how many integers commute with every other integer under addition?
All of them.
So in that case, the center of the integers, that's going to be my third example, Z of Z is going to be the entire group. So in that case, the center turns out to be the improper subgroup, just made up of everything. Which, in general, anytime you have a group, an abelian group, a group that's always commutative, where the operation is always commutative, the center is just going to be the whole group.
So we define it as like the largest subgroup that has it? Because like...
It's the set of all possible elements that commute with everything. Yeah. It has to contain all of them, otherwise it's not clear. Let's see, what else do I have? Turns out, if we were to look at the dihedral group on a square, the center is going to contain two elements. It's always going to contain the identity. It's going to contain the identity. And it turns out R squared will also commute with everything, with all the other symmetries of a square. It commutes with S, it commutes with R, it commutes with any combination of R's and S's, R squared. But not R, for instance, since, as we've seen, SR does not equal RS. So that's enough to immediately say, since S and R do not commute with each other, meaning SR and RS are different symmetries, that's enough to tell you R and S individually automatically cannot be in the center. G3, on the other hand, is going to have a trivial center. Dihedral group on a triangle, no element commutes with everything else in the group except for the identity element. The transformation where you pick something up and put it right, where you pick up the triangle, put it right back down. So depending on what group you're looking at, the center of a group may be the entire group. It may be the improper subgroup, it may be the trivial subgroup, or in the case of D4, it may be something in between. So the center will always form a subgroup, but it doesn't necessarily form a subgroup that's different than the other kind of examples of subgroups. It's going to be a future, I'm going to give it to you as a future homework question to find out what the center of the GL2R is. Any questions or comments so far here? Okay, next type of group, the centralizer of an element. So the center of a group in general is just going to be the set of all things in the group that commute with everything. If you restrict yourself to looking at a specific element, it turns out that the set of all group elements that commute with your fixed element is also going to form a group, called the centralizer of that single element. And here, because we like being confusing, the centralizer is going to get the letter C, whereas the center of a group does not get the letter C, it gets the letter Z. Go figure. So C of A, in general, is going to be the set of all elements G in your group, where AG is equal to GA. So let's say we're in D3, for instance, and we wanted to look at the centralizer of the element R. What's going to be some element in D3 that commutes with R? Some x such that XR is equal to Rx. What?
R.
R is always going to, any element is always going to be in its own centralizer. Because R times R is always going to be equal to R times R. Yeah. What else is going to commute with R? Identity element's always going to be in there because the identity element always commutes with everything.
R squared.
R squared is also going to be in there because R times R squared, R squared is going to be the same as R squared R, which is just the identity element either way. And it turns out that's it. S, RS, and R squared S are not going to commute with R. And so the centralizer of R in D3 is just going to be this subgroup that's made up of only rotations. So. Let's say let's look at a GL2R example here. What would the centralizer of the identity matrix be in GL2R, do you think? In other words, which elements of GL2R will commute under multiplication with the identity matrix?
Isn't it the entire group?
Why is that?
Because anything times the identity matrix is just the same matrix.
Yeah, take any matrix A in GL2R will commute with the identity matrix, because identity times A will always give you A, which is the same as A times the identity. So in this case, centralizer of the identity matrix will be the entire group, GL2R. In general, if you were to take, given any group, if you were to take something in the center of the group, so if, let's say, A is an element in the center of your group, what can we say then about the centralizer of A? So if A is in the center of the group, meaning A commutes with everything, what's going to commute with A? Everything. So if you take the centralizer of something already in the center is going to be the entire group. Something that's not in the center, though, if you take its centralizer, is going to give you a proper subgroup. Like with R. R, we said, was not in the center of D3, and so its centralizer ended up being some of the group elements, but not all of them. Yeah, you got R itself, the identity, and R squared, but nothing involving reflections. So these are always going to give us subgroups. The center of any group is a subgroup of the group. Give it any group at all, pick any element in that group. The centralizer of that element will be a subgroup of the whole group. It may be that the centralizer of an element or the center gives you the entire group, or maybe it only consists of the identity element, but it will give you a subgroup, guaranteed. Dr. KG, seal of approval. What questions do you all have about any of these? These are all examples that are going to be important to us kind of throughout the semester, ones that we're going to often be referring back to. Okay, page 3. So another group is going to be the group generated by an element. So given any fixed element A and G, the set, which we're going to define by putting sort of these triangular brackets around. The group generated by a single element is going to be defined to be the sum of all elements of the form A to the n is the group generated by A, which will be a subgroup of G. A to the n here, just so you know. Yes, Roy?
Sorry.
You can ask, what does A to the n mean?
Yeah.
So in general, when we mean A to the n, what we mean is A star A star A star A with n copies of A. So basically, A to the n does not literally mean taking A and raising it to the nth power, which doesn't make sense for a lot of groups. It just means applying the group operation to itself over and over again.
Why do we make n an element of the integers rather than the naturals?
Because we need inverses.
Yeah.
So in general, if we take A to a negative power, that just means taking A inverse star itself in copies of it. So if you take A to a negative integer power, that just means take A inverse star itself however many times you need. And finally, that covers all positive integers n and all negative integers n. What do you think it means to take A to the 0 power?
1.
Under the normal rules of exponents, that's what it would mean. But I don't think it would make sense to say, all right, I take the rotation in D3R, take it to 0 power, and it's going to give me 1. 1 is not a symmetry here. Right?
Your identity element?
Yeah. It's just, A to 0 is just going to be defined to be the identity element. You have no copies of A, kind of what's the base that you start with? It's just. So if your group is, say, a group under multiplication, like let's say the non-zero real numbers under multiplication, then A to the n works exactly the same way you usually think of as taking something to the nth power. And in that case, A to the 0 would be 1, just like how you might want. But if your group operation is not multiplication, in general, when we say take something to the 0th power, we really just mean it's the identity element. And so, in other words, if you take the group generated by A is just going to be A star itself any number of times, A inverse star itself any number of times, and the identity element, if you throw all those together, that's going to give you a group called the group generated by A. And in fact, this group is going to have a nifty property. It's going to turn out that this has a property that it's the smallest subgroup of G that contains A. Smallest here meaning if A is in any other subgroup of G, then the group generated by A also has to be a subgroup of that other subgroup. So if H is a subgroup of G and A is an element of H, it has to be the case that the group generated by A has to be a subgroup of H. Any other subgroup containing A has to contain its subgroup. The reason is because in order to have closure, if A is in a subgroup, you have to have A star A in order to have closure, right? Someone nod. Thank you. So in order to have closure, we have to have A star A, but we also have to have A star A to have closure. Because A star A is in your group, A star A is in your group, so you have to have A star A. And since A and A star A are in your group, you have to have A star A, and so on. Meaning, if you're a subgroup and you contain A, you have to contain everything of this form. In order to be a subgroup, you also have to have inverses, though. So if you have A, you have to have A inverse. And if you have A inverse, you have to have A inverse star A inverse, and so on. So inverses guarantee you have A inverse, and closure again guarantees you have to have any number of copies of A inverse. And finally, you need an identity element in order to be a subgroup, because part of subgroup is group, and group requires identity. So you have to have the identity as well. So I didn't write any of this down, but that's kind of your proof that if you're a subgroup that contains A, you have to contain all this other stuff as well. Baggage that comes along with A for the ride. Do an example. Let's say that we're looking at the integers, and I want to look at the subgroup that's generated by 2. What are going to be some elements in a group generated by 2? According to this definition of what it means to have a group generated by a single element. Everyone?
Do you want examples, or I think
Let's start with a couple examples, and then we can get to the whole thing.
4, 6. ...
You have to have, it turns out, this is going to be R2 to the first, this is going to be R2 squared, this is going to be R2 to the third, this is going to be R2 to the fourth. Don't go into your other math classes and say 2 cubed is 6, by the way. But what we really mean here is we're not saying 2 times itself 3 times. Here, when we use this notation, what we really mean is we're adding 2 to itself 3 times, because addition is the group operation here. So it turns out we're going to get all the positive multiples of 2.
Sorry, do we have to specify addition was the operation, or is that implied in the...
It's implied. Here's where you're getting into. Once we talk about a group example like a couple of times, I'm going to stop saying what the operation is each time. Technically, the integers by themselves are not a group. What I really mean is integers under addition. But since the integers don't form a group under multiplication, saw that the first day because it doesn't have inverses, it's kind of understood that if we're talking about the integers as a group, it's only a group under addition, so we kind of just drop it. Unless it's ambiguous and you have a set that can be a group under multiple operations. We also have to have 2 inverse. What's 2 inverse in this group, by the way? so we're going to have -2. That's our 2 to the -1. Again, don't say this in other math classes. We'll have 2 to the -2, which is -4, -6, -8, and so on. We also have to have 0, which is our 2 to the 0. Rowan, sounds like you have a nice way of summing this up succinctly.
I think it's just 2z from earlier.
It is. Turns out that the subgroup generated by 2 is just going to be 2z. And in general, in the integers, the subgroup generated by any integer n is always just going to be equal to nz. They're basically the same logic. How about this one? Let's say NGL2R. Uh-oh, I didn't specify a group operation. What's our group operation here?
Multiplication.
So again, GL2R, since it's only a group under multiplication, I'm not going to specify in general GL2R multiplication in the future, because it's just kind of understood that that's the group operation. So if I ever say in GL2R, what's the subgroup structure of blah, 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 I mean under multiplication. I want to look at this thing. The group generated by the matrix 1101. Well, I'll do the hard one. That's the hard one. The matrix itself is in the subgroup generated by itself. What else do we need in there? You don't have to say what it is as a matrix. You could say something to some power, for instance. Wayne, what are you giving me these looks for?
The identity.
You have to have the identity. We have to have 1101 to any positive integer power. Turns out it's going to be 1n01. Something you can prove if you want. Nice. If you've seen mathematical induction before, Greek students, I know you have, then you could actually, this is something you can prove with induction. You also have to have things of the form to negative natural numbered powers. So it turns out that the subgroup we end up getting here, and you can play around with this some if you'd like, is just going to be the set of all matrices of the form 1, n, 0, 1, where n is allowed to be any integer. And it turns out that is a subgroup of GL2R, and it's going to be the subgroup that's generated by this single matrix, 1101. Yeah?
How would you do a matrix like that to a negative power?
First of all, you take the inverse, and then you take the inverse to the nth power.
Okay.
So it turns out the inverse of this is just going to be 1, negative 101. So once you take the matrix inverse, you just multiply that by itself n times. And that's how you would take the original matrix to a negative n power. Same thing, same basic operation that we have here in this a to the negative n thing. There's multiplying, or you're just doing the group operation with the a inverse over and over and over again. Any other questions or comments? All right, well timed. That's what I was hoping we did today. When we come back on Monday, you might notice there's a few pages left in this packet. We're going to prove some theorems related to how can you prove whether or not a subset of a group actually forms a subgroup. Turns out you don't always need to go through and check all four group operations. Under certain circumstances, you can get some of them for free. Have a good weekend, everybody. See you all on Monday.
Yeah, quick question. Why does GL2R, why is that not a group on rotation?
So you're.
It does, for one, it doesn't have an identity element. The identity element would have to be the zero matrix,
Nice.
which is not an invertible matrix, and GL2R is only an invertible matrix.
Okay.
And also, it doesn't have closure either, which you can play around with by basically doing the fact that the sum of two invertible matrices is not necessarily invertible.
So,
General linear group. So GL is just general linear. And I don't know where the name general linear group comes from originally, but it's just the group of invertibles.
okay.
But I'll just text my name like.
That'd be great. Monday and
Oh.
Friday.
Class over, I can stop the